Okay, so let's work on the vibration and rotation case. So again, right, previously we have learned the different scenario for quantum system, right, at different confinement. And here we're going to consider another case, which is the vibration. So for vibration, we know the simplest case is a harmonic oscillator. And in that case, right, if we just think if it's a vibration of a single particle, usually what's going to happen is we actually should have a x and we have a potential, right? We have a particle lies within the potential. So then you have a kinetic energy of the particle, or we have a speed of the particle. And of course, it's a particle gonna, right, oscillate within this symmetric potential well. And similarly, right, even it's not a single particle, for example, it's a diatom molecules. You have this diatom molecule either stretch or compress. And in that case, right, what we can name is rather than the position, but in this case, we use the displacement. And for that case, right, it still can be treated. Of course, for diatomic molecules, right, we know the potential normally falls onto like this. So when they get close very together, right, you have the very large repulsion force. And at a certain stage, right, you actually have the attractive force. Of course, this is not similar to the harmonic oscillator. But let's say if, right, the vibration are concentrated in a, right, the concentrated on surrounding the equilibrium place. So in that case, this part, right, can be actually approximate into the harmonic oscillator. Okay. So everyone knows, right, Fick's law. We know the with the note, right, the force equals to the force constant times the x. And since for the energy part, right, or the potential energy part, the force actually equals to minus derivative of the potential energy divided by derivative of the displacement. So you can write down that dv equals to minus the force times dx. And from here, we do the integration, right? We do the dv equals to integration f dx. So the dv integration is v, is the potential energy. That equals to minus f. And here, the f is minus kf x dx. So we do the integration. You actually have integrate kf x dx. So in that case, integrate of the x, right, it should be 1/2 of kf x squared. So in that case, we actually know, right, the expression of the potential energy in the oscillator, right, where is equal to 1/2 kf x squared. So now let's consider, right, if we have a particle inside this harmonic oscillator energy well, right? So in that case, again, right, if we want to know the behavior of this quantum system, what we're gonna do is to solve the Schrodinger equation. The first step, of course, is to, right, to actually write down, right, as I mentioned, right, the mathematical expression of the potential energy. And now the first step we already have. And the second step, right, is to actually look at whether we can find a similar simple system into, right, to replace this system, and apparently no. So what we can only do is, right, to actually plug in this potential energy into the Schrodinger equation. And now we have the Hamiltonian operator equals to the kinetic energy part plus, in that case, the potential energy part, since we have already known, right, it's a kf x squared. So this is a Hamiltonian operator. And then we can write down the Schrodinger equation based on this Hamiltonian operator. That's the operator applied on the wave function equals to the total energy times the wave function. And in this case, right, the operator is 2m d squared dx squared plus 1/2 kf x squared. And from here, we apply this operator onto the wave function, and we get e phi x. And of course, what we're going to do is to solve it. And apparently, right, this is definitely much more complex, right, to solve. But what we can do is actually we can make a guess, right, what the wave function should look like. And if you look at this potential energy well, right, it's actually a symmetric potential energy well. So if, right, it's a symmetric potential energy well, and we should assume, right, the wave function that we saw should also be a symmetric one. And if we want to have a symmetric distribution of probability density, right, it might just be like a Gaussian distribution or Lorentz distribution, right, the normal distribution. So in that case, what we can do is just simply guess. Right, the simplest case, right, the wave function at ground state, right, should follow a Gaussian function. And your Gaussian function can be expressed as e to minus ax squared. And if we actually try to solve that, you'll find, right, at least for the ground state, you'll find this actually follows the Gaussian distribution. You have to learn about that, right? You have to, I don't expect you to solve, but at least, right, when you say a symmetric potential, right, you should also assume or conclude that the distribution should actually be a symmetric one. And of course, if you're using those calculator or software to do the calculations, you will find we're able actually to solve the eigenvalue, right, of this Schrodinger equation. So the solution actually gives us is the vibration energy actually equals to V plus 1/2 times h bar and 10 times kf divided by m square root. And here, what we can do is to introduce omega, the frequency, and it's actually equals to kf divided by m, right? Square root. That's what we learned from the harmonic oscillator or the spring. And what you get is the vibration energy equals to v plus 1/2 times the h bar times omega. Omega is simply the frequency. And the v here is actually a quantum number that we saw, right? That's the vibration quantum number. And if you look at this, right, you will find the vibration energy is also quantized. And if we look at that, right, we can find if we have a potential energy well, like this, and we know, right, the potential energy distribute in a symmetric way. That's the potential energy. And for the energy, right, vibration energy of the quantum system, we actually have them equally spaced. And you have the v equals to 0, v equals to 1, v equals to 2, v equals to 3, v equals to 4, v equals to 5. And you'll find, right, the difference between each energy level is equally spaced. And this is apparently different from the particle in the box case, right? Again, right, for the particle in the box case, we know the energies are also quantized, but their energy difference between each quantum level, right, is not equally spaced. But for the vibration, at least in a harmonic oscillator vibration, right, for a quantum harmonic oscillator, right, you actually have a equally spaced quantization of the energy. Another thing, right, we can conclude from the expression of the energy is that we have a 0-point energy. And the 0-point energy is not zero. Right, so that means, right, even we cool down the system to absolute zero temperature, right, there's still a vibration can happen in a quantum system. And if you still remember about the uncertainty principle, right, you know that, right, even at very low energy temperature, right, there still should be some fluctuations, and that's why you get the vibration energy. And again, right, all you require to remember or know is this, right, quantization of the energy, this equation. You need to know how to apply that, right? I might just ask you, right, what is the energy difference between different quantum numbers for the level, right? Okay, so let's move on, right? And then, of course, we want to know what is the wave function look like. So for the vibration one, again, I don't really require you to know the expression. You just need to kind of have a understanding that's equal to a vibration e to y squared divided by 2. and y equals to x divided by 2, and here divided by alpha, sorry, this is alpha, and the alpha actually equals to h bar squared divided by m kf power 1/4. So that's the vibration harmonic oscillator. Okay, then we can move on.